Dear students, welcome to the third session of our chapter 6 Thermodynamics. In this session, we will deal with the topic enthalpy or heat content, and it is denoted by the capital H. The energy stored within the substance or the system that is available for the conversion into heat is called enthalpy or heat content of the substance. So, what is the enthalpy? It is the energy stored within the substance which is converted into heat. It is denoted by H and related to the internal energy U through a mathematical equation. H is equal to U plus PV. U is internal energy, P pressure, and V volume. Enthalpy is also a state function. It has a definite value depending upon the state of the system and is independent of the path by which the state is reached. That's why we are giving the equation H is equal to U plus PV. If you want to write the change in enthalpy, the change can be represented with delta. So we'll write delta H. This is what change in enthalpy is equal to delta U, change in internal energy, plus PV is there. So both the cases at constant volume and pressure we can write. So we'll write what? P delta V plus V delta V. At constant pressure, delta P is equal to what? 0 we are taking. At constant pressure, delta P is equal to 0. Then how we can write the equation? Delta H is equal to delta U plus P delta V. So this is the equation which we are using for our problems. Thus, the increase in enthalpy, that is delta H, is equal to the heat absorbed in a process at constant pressure, when only the pressure volume work, that is P delta V, is done. When only the pressure volume work is done. So long as the system does no additional work, the heat supplied to a system at constant pressure is equal to the change in enthalpy. So how we can write that equation? That is delta H is equal to QP, that is at constant pressure. So the enthalpy change for a chemical reaction where the reactant gives you product, how we can write? Delta H is equal to H product minus H reactant, that is enthalpy of the product minus enthalpy of the reactant. This is how we can represent the enthalpy change for a chemical reaction. There are two cases. When the heat is absorbed, Q is positive. Therefore, delta H is also positive. And in this process, where the delta H is positive, it will absorb the heat. So, such processes are said to be endothermic process. And when the heat is evolved, that is Q will be negative. So, delta H also will be negative. The process where the delta H is negative, it will give out heat. It will give out means it will liberate some heat. So such processes are said to be exothermic processes. So these are the two conditions where the heat is absorbed and where the heat is evolved. We can define the endothermic process and exothermic process. Standard enthalpy change. Enthalpy change we know that is delta H. If the word standard comes, we have to understand the change is there in the standard condition. So how we can define is, it is the enthalpy change for a reaction when all the participating substances are in their standard states. And what is the standard condition? The pressure should be 1 atmosphere or 1 bar. Then temperature should be 298.15 Kelvin. These are the two conditions where we are saying it is in standard state. And the standard conditions are denoted by adding a superscript. We usually represent 0 to the symbol, and we represent that standard condition. So here we are using delta H and the superscript 0. So we will read it as what? Delta H0, which is named as standard enthalpy change. So wherever the 0 represents along with the symbol, it is in the standard condition. Next, we have to see the relationship between delta H and delta U for an ideal gas. Delta H is the enthalpy change and delta U is internal energy change in internal energy. So we have to bring a relationship between these two terms. So how? We have to take a reaction. We have to take a gaseous phase reaction where the temperature and the pressure are constant. So let's see a reaction AA plus BB giving CC plus DD. Let's take NR as the number of moles of the gaseous reactant, that is A plus B, the coefficients. NP, the number of moles of gaseous product, that is C plus D, small letters. Then capital VR is the total volume of the gaseous reactant, whereas VP is the total volume of the gaseous product. Now we know the ideal gas. What is ideal gas law? That is PV is equal to nRT. So for the reactant side and the product side, we can get the equation. So how we can write? PVR is equal to nRT for the reactant part. For the product side, we will write PVP is equal to NPRT. Taking the P terms common, we will write PVP minus VR is equal to NP minus NRRT. What is this Vp minus Vr? It is the change in volume. So we can write P delta V. And Np minus Nr is the change in number of moles of the gaseous phase. So we have written here delta Ng RT. But we know that delta H is equal to what? Delta U plus P delta V. This expression we have brought before. So from this, we can just substitute the P delta V. This equation, if we substitute P delta V, how we can write? Delta H is equal to delta U plus delta Ng RT. That is, instead of this P delta V, we have written delta Ng RT. So the equation is changed to delta H is equal to delta U plus delta Ng RT. This is a relationship in the gaseous phase for an ideal gas. Next, we have to deal the topic measurement of delta U and delta H. For that, we have to see the next topic, that is calorimetry. It is an experimental technique to measure the energy changes associated with physical and chemical processes. And the vessel which is used for this calorimetry is said to be calorimeter. Calorimeter. Now we have to discuss the bomb calorimeter. A steel vessel, which is named as what the bomb here, is immersed in a water bath. The whole device is said to be what? Calorimeter. A full steel vessel is there which is immersed in a water bath, and it's full. Along with the water bath, we are saying it as what? Calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost to the surrounding. No heat is lost to the surrounding. A combustible substance is burnt in pure oxygen supplied in the steel bomb. The heat evolved during the reaction is transferred to the water and around the bomb, and its temperature is monitored through thermometer. Since the bomb calorimeter is sealed, its volume does not change. That is, the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V is equal to 0. The temperature change of the calorimeter produced by the completed reaction is then converted into heat. You can see the diagram where the steel vessel is there which is immersed in the water bath. Other outer container is there. Inside this water is there. This is what the steel vessel which is immersed in the water. Here a thermometer is there to monitor the temperature. You can see the oxygen inlet through which the oxygen is supplied to the steel bomb. This is what a stirrer to just stir the solution. Sample is there, that is oxygen under pressure is kept. The bomb means the steel vessel is said to be the bomb. The firing leads are there, that is leads are there, that is what the rods which conduct the electricity. So this is a calorimeter through which we can understand the change in heat energy. Let's see the next one, reaction enthalpy. In a chemical reaction, the reactants are converted into products and is represented by reactant giving products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change accompanying a reaction is said to be reaction enthalpy, and it is given as what, delta HR. Delta H is change in enthalpy of the reaction is what, R representation. So it is what, sum of the enthalpy of the product minus sum of the enthalpy of the reactant. And how we can write in mathematical way, sigma AI H product minus sigma BIH reactant. Here the sigma is used for the summation, that is for the addition or the whole sum, and Ai and Bi are the stoichiometric coefficients of the product and reactants respectively in the balanced chemical equation. So this is what the reaction. And let's see the enthalpy changes during the phase transformations. First one is standard enthalpy of fusion, or the other name is molar enthalpy of fusion, and it can be represented as what, delta H0 fuse, FUS. It is the enthalpy change that accompanies melting of 1 mole of a solid substance in standard state. Melting means itself, we know that solid to liquid conversion is there. So the phase conversion is there from solid to liquid. And there the amount of energy required for 1 mole of solid substance to change into liquid form at standard condition is said to be standard enthalpy of fusion. Same way, the next one is standard enthalpy of vaporization. So how we can represent, delta H0 VAP, that is molar enthalpy of vaporization, and it can be defined as the amount of heat required to vaporize 1 mole of a liquid at constant temperature and under standard pressure or standard condition. So this is what standard enthalpy of vaporization. And the third one is standard enthalpy of sublimation, delta H0 SUB. It is the change in enthalpy when 1 mole of a solid substance sublimes at constant temperature and pressure. So these are the 3 phase transformations where the enthalpy changes are required or changes are there. So this is about the 3 transformations. Now next one is Hess's law of constant heat summation. How we can define is, if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. The law states, if a reaction takes place in several steps, then its standard reaction enthalpy is the sum of the standard enthalpies of the intermediate reactions into which the overall reaction may be divided at the same temperature. More explanation if we want for the Hess's law, we can explain through an example. That is, suppose if we in a reaction, the reactant A changes to the product B in one step, and the heat change during the process is what, delta H0R, that is reaction enthalpy. And suppose we are having the same process which is carried out in 3 steps, then there is 2 different reactions. It's the same reaction but in 2 different ways if we are conducting, we can explain the Hess's law. See the root 1 and root 2, what it is mentioning. Here in the diagram you can see A, B, D and C, right? This is what A to B, that is the reactant changes to B in one step, that is root 1. The same thing if it is happening in 3 steps, that is step 1 A to C, step 2 C to D, Step 3, D to B. It happens in 3 steps, that is root 2. And what we are going to explain is the reactant A changes to C. The enthalpy change during that step is delta H0 R1. Same second one, delta H0 R2, delta H0 R3. Three enthalpy changes we are getting. According to the Hess's law, we have to write the delta H0 R is equal to all the three enthalpies, that is the intermediate reactions sum. We have to write the enthalpy change. So it will be what, delta H0 1R plus delta H0 2R plus delta H0 3R. All the three enthalpies we have to add up and get the reaction enthalpy of the reaction. So this is said to be what, the Hess's law. Here the application is there. In one step or the three steps if it is carrying out, we are getting the same reaction enthalpy. Thank you. We'll continue in the next session.